it's the top of the hour, 7 o'clock, so let's get started. Welcome to the Vashon Heritage Museum History Talks, and this first of a special 8-part series of talks on Vashon 101. The original Vashon 101 was the vision of lifelong, or had a vision of lifelong learning, was the inaugural event for Vashon College in 2006. Tom and Melissa Bangisser, along with several others, and the original board of Vashon College, with help from the first faculty, all came together to imagine and create the series to offer to the community. Our talk tonight is presented by Steve Bergman on Vashon Geology. I'm Elsa Kronquist, the Executive Director of the Vashon Heritage Museum, and I'd like to start the evening by recognizing some of our sponsors of our history talks and say thank you to For Culture and Humanities Washington and all of the speakers who will be presenting throughout this 8-part series, specifically this evening, Steve Bergman and Patrick Christie. Keep in mind that if you have any questions during the presentation, please put them in the chat function and we'll answer questions during the discussion at the end of the presentation. This is a webinar, so you will be able to see the presentation. You will not be able to see others, and you won't be able to talk to anyone else except through the chat function. Let's see. Also, this talk and almost all of our talks are recorded and can be found about a week after the presentation on the Vashon Heritage Museum website. Let's switch to the next slide, please. As is our museum's tradition, we begin all of our presentations with the land acknowledgement statement. I would like to introduce Chris Austin, a museum board member, to read our statement.
Thank you, Elsa. The Vashon Heritage Museum stands on the ancestral lands of the Shwabops, or Swiftwater people, who inhabited Vashon Maury Island for millennia. The Donation Land Claim Act encouraged large numbers of Euro-American settlers to claim this land, even before the Medicine Creek Treaty of 1854 extinguished native claims to it. The Shwabops were forcibly removed and relocated onto nearby reservations, including Puyallup, Nisqually, Squaxin Island, and Muckleshoot. We acknowledge the people of the Puyallup tribe whose stewardship of and relationship with Vashon Maury Island continues today. We commit to amplify the voices of Indigenous people, making space for them to tell their own story, both past and present, in our exhibits and programs. Now, Elsa, would you do the inclusion pledge, please?
Be my honor. Thank you. The Vashon Maury Island Heritage Museum rejects racism, discrimination, and hate. Our purpose is to honor stories of love, oppression, action, and resilience. Stories that give voice to all, examine hard questions about social, economic, and environmental justice, and reveal racism and oppression within our heritage. We pledge that everything we do will honor the island's diversity of cultures and histories. At this time, it is my honor to introduce Patrick Christie, who will introduce the series and tonight's speaker. Patrick has lived on Vashon since 2001. He was trained as both an aquatic biologist and a sociologist at the University of Wisconsin and University of Michigan. He started his career as a U.S. Peace Corps volunteer working in a Filipino community to protect and restore a coral reef. He is now a professor at the University of Washington, where he studies and teaches about how people relate to the ocean and how we can best organize society to improve sustainability. He is also an activist who has worked with others on this island to prevent the establishment of a massive gravel mine on Maury Island. He has the privilege of learning from and working with Indigenous leaders in Minnesota and locally who are committed to addressing the environmental and climate crisis we face. When he's not working abroad, he loves to play jazz as a bassist and to garden. He'll help coordinate the series and work with the speakers and students to identify themes and opportunities that emerge from Vashon 101 to improve our community. Welcome, Patrick.
Thank you so much, Elsa, for that warm welcome. And it is truly an honor to be here with everyone tonight. So I'm going to just make a couple comments about the course and then pass it on to our speaker, Steve, tonight. So I think Vashon 101 is above all an important community building event. As you see, the talk series covers a wide variety of topics, and most notably, we are honored with the presence of two Indigenous teachers who will offer us a deeper understanding of this place we call Vashon and Maury Island and the surrounding areas. Let's keep in mind that the land acknowledgements in their best form go beyond acknowledging the original inhabitants of a place, as important as that is, to expressing our commitment to positive change by supporting Indigenous peoples and their rights as allies. We are the allies with them. We have much to learn from one another, so we invite you to be an active participant in this Vashon 101 to learn from and alongside our speakers. Practically, I invite you to look for overarching themes as well as unexplored topics that we might consider in the future as you listen to each of the speakers. These themes will form the backbone of the final session that I'll be coordinating. Let's commit to taking what we learn to improve Vashon and our relations with those we know and those we may not have the privilege of taking, who may not have the privilege of taking this class or living here. For me, the themes like sustainability, equity, and how history shapes our society will come to the forefront. I invite you to identify other themes that resonate with you. So in short, I believe I speak on behalf of all of the speakers when I say we look forward to learning together and using this opportunity to grow and improve the place we call home. So I now have the privilege and honor of being able to introduce our inaugural speaker this evening, Steve Bergman. Steve will present to us on Vashon geology. Dr. Steve Bergman joins us and has lived on Vashon Island since 2014 and is what he refers to as a geoactivist. He currently serves on the board of directors of two nonprofits on the island, Zero Waste Vashon and Vashon Makerspace, and participates in local geology activities, including curating the native rock garden and geology portion of the Heritage Museum Wonders exhibit. And we look forward to learning from you, Steve. Thank you so much.
Well, thanks, Patrick, for that introduction. And thank you, Elsa, and the rest of the museum for sponsoring this series. I'm really looking forward to a fantastic series of talks. And thank all of you for joining us tonight. My purpose today is to try to provide a grounding for the entire series and talk about the geology, talk about what lies beneath our feet, some of the geologic hazards that we have. And I would hope that you walk away with the view that every beach rock that you walk on tells a really cool story. And this is sort of building on what you might have already seen at the Heritage Museum, the Natural Wonders exhibit outside in the back. It's open 24/7 for anyone that hasn't been there, so you don't have to come during office hours to see the exhibit. So we live in a very special place, and I'm really trying to focus on why Vashon is the way it is. And I thought we'd start off in the big picture and look at the blue marble that the Apollo 17 crew viewed from outer space back in 1972 and saw what the Earth looks like from far away. And on the right, we see what lies beneath our feet in the interior of the Earth and how it's layered. The center, the very center of the Earth is as hot as the sun's surface, which blows me away every time I think about it. It's white hot. If we could see it, it would glow white, just like the sun. But it can't, because there's a lot of rock in between the outer core, which is liquid and convecting, and the lower mantle, which is also convecting in the solid state now in the mantle, which is a little different than the liquid outer core. And above the mantle, we have the crust. And so you can see that as we go toward the interior of the Earth, it gets denser with iron nickel forming the core, and a dense peridotite mantle overlain by a thin crust that's either oceanic or continental in composition. Oceanic crust is different than continental crust, as we see in the next slide, that shows a little closer look at the Earth, the topography and bathymetry of the Earth's continents and the ocean. And at first glance, you might think that the Earth is like a yin-yang, but in fact, it's really not, because the Earth's continents and the oceans, even though they're a dichotomy, are both good, and neither are evil, like the yin-yang would have it. So the continents are riding on the mantle, and they are moving around. They're dynamic. This is the present day situation on the right, but in the past, they have occupied different positions. And if we go back 200 million years, we would have seen the supercontinent Pangaea, with the paleogeography shown on the left here. Vashon is about right up here. And you can see that each of these plates is shown. The North American plate is shown here. This is the Paleo-Pacific plate, called the Farallon plate. And you can see South America and Africa, parts of Asia, all forming this big supercontinent that broke up at about 200 million years ago to form the present day mid-Atlantic ridge in the Atlantic Ocean. And at the time, the Pacific Ocean has been shrinking since that 200 million years. Now, we don't have time to go in and show how these plates are actually moving around, but you can download this great app for free on the web. It's called Earth Viewer, and it's done by the Howard Hughes Institute at this website. So I urge everyone to go download it, and you can move the continents around and see how they've moved through time. It's really a nice feature. So this is what the plates look like if we flattened out the Earth on a map in this particular projection, this Mercator projection. And you can see that all the plates, the 13 major plates, are colored differently. We are sitting up here on the North American plate, and you'll see V either in green or in blue in a lot, or in purple in a lot of the slides coming up. That shows where we live on Vashon here. You can see that we're on the North American plate, but we're right next to the Juan de Fuca plate, which is being subducted to the east beneath North America. You can see that we have 3 types of plate boundaries, the spreading ridges that are shown in this pattern, the subduction zones that are shown in the teeth pattern here. We do have a subduction zone here, even though it's not shown on this particular map, because it's so the subduction zone is so small relative to all these other ones, like over in the South Pacific and in Eurasia. So these are subduction zones along these boundaries. And then we have the strike slip fault type of plate boundary that is shown with these black lines, like the San Andreas fault here, the Queen Charlotte fault up here, and a number of other strike slip faults or transform faults that occur around the plate circuit. So these plates are moving really slowly in our human sense, in fact, about the rate our fingernails grow. But in geologic time, they move great distances. Over millions of years, they move hundreds of kilometers or even thousands of kilometers. And so that is what brings us into this next slide, which is geologic time, the deep time we call it. And we've taken 4.5 billion years of the history of the Earth and put it in a 12-hour clock here. So here's the origin of the Earth 4.5 billion years ago. And as we go clockwise, we see the major biological events that have impacted the planet, the formation of bacteria 4 billion years ago. Anoxic photosynthesis started back 3.8 billion years ago. Nitrogen fixation bacteria started 3.2. And then it wasn't until about 2.4 billion years ago that the world changed. Prior to this time, we had carbon dioxide and nitrogen forming the atmosphere, but we had oxygenic photosynthesis start about 2.5 billion years ago. And suddenly we have oxygen in the atmosphere. The oceans changed from green to red, from red to green, and just an amazing change in the world because all of the anoxic bacteria that were living in the oceans suddenly went extinct. We had a huge major extinction because of the presence of oxygen. It killed them all off. And since that time, for the last 2.5 billion years, the oxygen concentration in the atmosphere has varied from 10 to 25%. When it gets too high, we have lots of fires. When it gets too low, life has a hard time, and it's varied just because of natural processes of rock weathering and other processes. And then we go ahead in time, and we are at about 2 billion years ago, and fungi formed. We had multicellular life forming about 1.5 billion years ago, mitochondria 1.45 billion years ago. And it wasn't until about 750 million years ago that the first single cell animals formed. We had a snowball Earth just after that for several million years, actually several hundreds of millions of years, where the entire Earth was covered by ice. And it wasn't until volcanoes burnt out enough carbon dioxide that the atmosphere had a greenhouse effect, and we were able to warm up the planet enough to melt the ice. There were several different ice ages in the Phanerozoic. And as you can see, in this entire Phanerozoic period, which is the last 540 million years, a lot has happened. A lot of land plants, animals, diverse life forms have evolved, and we've had 5 major extinctions, 4 of them natural extinctions caused by meteorite impacts or large volcanic eruptions. And the most recent one that is right here at the present day is caused by us because of our actions that have totally impacted the planet, caused major extinctions for a number of organisms on the planet. So it's just amazing how 4.5 billion years has seen such a fantastic evolution on this planet. So let's jump into what the Earth looks like beneath our feet here on Vashon. Here we are looking at a cross-section, an oblique cross-section. Here's V for Vashon. And so this is what it looks like beneath our feet if we were to look at it diagrammatically. The west is over here. Here's the Pacific Ocean. Here's east. This is looking into central Washington. And as you can see, we have the downgoing Juan de Fuca plate being subducted beneath North America. As it subducts, it releases water. That water causes melting of the upper mantle, which creates magma that rises up to form the volcanoes that we're all familiar with, like Mount Rainier, Mount Baker, and all the rest of the Cascade volcanoes. And because of this compression between the two plates, the accretionary prism, all the sediments that are being dumped into the ocean at this subtrench are being deformed and squeezed and folded. And over here, we have the creation of new oceanic crust where the Pacific plate is spreading away from the North America, or from the Juan de Fuca plate. And so we have two plates spreading apart. As these plates are moving away from each other, they passively cause upwelling of the mantle beneath, which melts and forms basalt lava that forms the oceanic crust that forms the ocean floor out here. And eventually, this lithospheric plate gets dense and it falls back in and sucks the plate down into the mantle. So these spreading ridges are passive. They are caused by the subduction of dense lithosphere in these subduction zones. The Pacific plate out here is moving up towards Alaska, and it's getting subducted beneath Alaska and Russia because of the slab pull effect of the dense lithosphere. You can see that we also have an old plume here that initiated about 16 million years ago to form the Columbia River basalts, and they are shown in this brown pattern here when we had massive fissure eruptions with lavas flowing all the way into the Pacific Ocean. You can go to Cannon Beach at Haystack rock and see bits of the Columbia River basalt that flowed over 500 miles to get to the ocean back about 15 million years ago. Today, that hotspot is forming the Yellowstone plume and the Yellowstone volcano, the big caldera that exists in the Yellowstone National Park. So we've had a very interesting history here in the last, just the last 20 or 30 million years. Another event that we're going to be talking about is the formation of Siletzia, which is a terrain that's shown here in this brown. These are 56 million year old basalts that formed originally out in the Pacific because of a large hotspot. And this oceanic plateau got accreted and plastered onto North America about 50 million years ago, and it forms our basement. It forms the core of Vancouver Island and Washington and Oregon. So the whole western part of North America, the northwestern North America, is formed by this Siletzia terrain that originally was out here in the Pacific before getting welded to North America. If we looked at the same place, the cross-section going north-south with Vashon right in the middle here again, you can see that the plate boundary is actually folded. It's folded because the Pacific plate is causing the North American plate to squeeze against Canada, and it's bending this subduction zone. And it's interesting that this is a 3-to-1 vertical exaggeration, so it's not as strong a fold as it's shown here. But you can see the complex geology that's above us. And you can see that we are bounded by two major faults, the Seattle Fault and the Tacoma Fault. And those are high angle reverse faults. And because of this north-south compression, the Seattle uplift on which Vashon sits pops up relative to the Seattle Basin and the Tacoma Basin. It makes Vashon a safer place to live than Seattle and Tacoma, because if we were to have a big earthquake, they would get a lot more shaking than we get because we're on more bedrock than they are. So it's interesting that Vashon is a good place to be as far as the rest of the Pacific, Puget Sound goes. So let's go into a little more detail on the faults. So Puget Sound has its faults, and here we are down at Vashon here, as you can see, and we have the Tacoma Fault Zone to the south of Vashon and the Seattle Fault Zone to the north. And these are both east trending faults. You can see they're perpendicular to the main plate boundary, which is shown out here, the Cascadia subduction zone. And again, it's because the Pacific plate down here with the San Andreas Fault, is causing this part of the North American plate to get squeezed to the north, and that causes these east-west faults to form. There's a number of other faults to the north through Whidbey Island, the Whidbey Island Fault, the Darrington Devil's Mountain Fault up in the San Juans, and all these are caused by the same process of north-south compression. And in fact, this whole block of North America is rotating to the north, clockwise around us and moving to the north. If we take a bigger picture view and look at, here's Vashon here in green, and we're looking at western Washington and northern Oregon here. All the dots are earthquake epicenters. The bigger dots are larger magnitude earthquakes, as you can see over here. And we're also showing quaternary faults, recent faults that sometimes some people have suggested that some of these over in the Yakima Fold Belt actually link up with the Tacoma Fault and the Seattle Fault and so on. And that's being studied right now to see if all these are linked up or not. But nevertheless, we do have our share of faults that could rupture and cause earthquakes. You can see that we live in a very dynamic place with a lot of earthquakes and a lot of faults. And this is just a more regional view showing our subducting Juan de Fuca plate beneath the North American plate. Here's the plate boundary out in here at the surface, and the plate boundary continues underneath us. It's about 45 kilometers below us here in Vashon. And you can see some of the major earthquakes that have happened. There's a lot of earthquakes that occur along these plate boundaries, and some occur within the plate. because of processes down below and this north-south compression. You can also see the distribution of all the volcanoes forming the Cascade Volcanic Arc, where we have subduction of the Juan de Fuca plate. And this is an amazing feature here. Over 500 kilometers of offset occurred during the Great Cascadia earthquake of 1700, a magnitude 9 earthquake that impacted the region. It was huge. It happened on January 26, 1700. And we know this for two reasons. One, because of some native indigenous legends that have been passed down, and also because in Japan, a huge tsunami was recorded that didn't have a known source. And by going in and studying some of the sediments in the Puget Sound, geologists have been able to find the tsunami deposits that were recorded here, and they've carbon dated them about 1700. And so with the Japanese record of the tsunami, they were able to backtrack it and know that it occurred at about 5:30 p.m. on January 26, 1700. Over 1,000 kilometers of the plate boundary was ruptured, and it caused a huge tsunami that devastated and caused a lot of deaths in the interior. Over a 10-meter wave would have impacted the coast. And so over the last 6,000 years, there's actually been 13 great earthquakes of magnitude 8 or 9 that have impacted the Northwest. If we were to have another magnitude 8 or 9 earthquake and a tsunami would form, most likely, it would take about 15 to 20 minutes for that tsunami to get to the West Coast. And the wave height would be on the order of 10 to 30 meters high, which would cause a lot of problems for anyone near the coast, which is why there's a lot of tsunami warning signs out there, what to do in the case of a tsunami. If you feel shaking, get to higher ground is the bottom line. It takes a lot longer for the waves to get into the Puget Sound through the Straits of Juan de Fuca and down the Puget Sound, and it would take nearly an hour to get here, and we would have maybe 5 to 10 meter waves at most, probably less, in a big earthquake like that. So that is one of our hazards of living in this beautiful Pacific Northwest. So how likely are major earthquakes here? We can go back in time and see major earthquakes that have happened in the past. There are 3 types of major earthquakes that we would expect to occur. A deep slab earthquake, like the Nisqually back in January in 2001, magnitude 6.8. Had an epicenter down, hypocenter down here that caused lots of damage in the Seattle area. And there were also similar earthquakes of a similar magnitude in 1965 and 1949. These are the most common type of earthquake that we have in this region. And so they're a lot more frequent. They're pretty deep. They're 40 to 50 kilometers deep, which means that it takes not as much energy gets to the surface because a lot is attenuated and absorbed by the 40 kilometers of crust between us. But in all probability, there's, in the next 50 years, an 85% chance of having another magnitude 7 earthquake here in the Pacific Northwest. We personally have earthquake insurance. We're thinking of canceling it because 85% in 50 years is not that, and I'm only going to live another 20 or 30 years, so it might not be necessary. The second most likely type of earthquake to occur is one along the Cascadia megathrust, which is shallower, and it's a much larger magnitude, but these are very infrequent. They occur about every 300 to 600 years, and there's only about a 15 to 25% chance of one of these earthquakes happening in the next 50 years. The shallow types of earthquakes that result from the movement on the Seattle or Tacoma faults usually can at most have a magnitude 6 or 7, probably much less. The largest historic earthquake of one of these faults was back in 1872, and they are the rarest of those 3 types, and there's about a 15% chance of one of these earthquakes happening in the next 50 years. So I went on the USGS website yesterday, and this is the distribution of the last month's earthquakes with the magnitude as much as 6.4 down here in California. that occurred within the last 30 days. And you can see that California has by far most earthquakes, and a bit in the Basin Range here in Nevada. We get our share. Alaska gets more than both California and Seattle, but it's also interesting that we see a lot of earthquakes over here. This is the New Madrid fault zone in near Missouri and Indiana and Illinois. But these earthquakes here are in the mid-continent, and they are caused by pumping wastewater down into wells and inducing seismicity. They're not that large. They're fairly small earthquakes, magnitude 2 and 3 at most, but they still cause damage. And a lot of the earthquakes you see here near Dallas and in the Permian Basin are caused by fracking activities, pumping the wastewater left over from the fracking back into the earth. And they're changing the stress field and causing earthquakes and causing damage to people's homes in these areas. So it's interesting that we have Mother Nature causing its share of earthquakes, and we have man's activities causing new earthquakes since the onset of a lot of fracking activities. So why is Vashon such a good place to be, as I mentioned earlier? Well, this is a map showing the Seattle Basin here. The darker colors are the deeper basin, and the Tacoma Basin to the south. And this is the result of a model to show how much shaking intensity we would have in the event of a big earthquake. And you can see that Vashon here with the V is in the safer zone with less shaking intensity compared to Seattle and Tacoma. So if you had a choice in the best place to live, the Seattle uplift here in the middle is the safest place, in my opinion. And in terms of the risk elsewhere in North America and in the United States, this shows that Seattle is pretty risky, not as risky as California here because of the San Andreas, a lot more active, but the most risky is up in southern Alaska because of the plate boundary up here. Hawaii is pretty risky because of the active magmatism that's going on with Mauna Loa and Kilauea recently erupting, and a lot of earthquakes happening there as well. Some of these other areas in the east are caused by basement faults that are reactivated by plate stresses, like the New Madrid fault zone in here. And there was a big earthquake in South Carolina back in the 1800s that was caused by reactivation of an old fault because of plate stresses, the North American plate being pushed both ways, causing internal deformation. So if you're interested in being warned about earthquakes, you can join the shakealert.org app. You can put it on your cell phone, and because the shaking, the seismic waves moving through the earth move slower than electrons moving through wires, you can be warned long in advance, many seconds in advance, sometimes minutes in advance of the actual shaking to hit you from a faraway earthquake. So you can go to shakealert.org. This is a fairly new app that's run live now for the Western US, and I think it's a good idea. If you do have a warning for a tsunami, and if you are close to the coast, seek higher ground. If you're near the shore, if in the Puget Sound in our area, you'd want to be at least 10 meters above sea level, 30 feet. If you were to receive a tsunami warning, but then you should be safe. But then we do have all the other damage that can occur because of earthquakes. They can take lives, destroy homes, businesses, public buildings. They can induce landslides. They can damage roads, interrupt transportation. They could break bridges, derail train cars, and damage utilities. They could cut power lines and cables. So we are very active here on Vashon with Vashon Be Prepared to be prepared for these types of earthquakes. So rest assured that that's being taken care of really well. So that's earthquakes, and now let's move into glaciers. During the last ice age, we had an advance of the Puget Lobe of the Cordilleran ice sheet move all the way down the Puget lowlands here, all the way down to Olympia. And it buried Vashon by over 1,000 feet of ice. And it caused all sorts of changes to our landscape. It caused all sorts of erosion. And It was here for a few thousand years, and then it slowly retreated. And as it retreated, it dammed rivers. Well, before it retreated, it dammed rivers, and it created these huge lakes, these glacial lakes to the south, because all the rivers are coming off of the Cascades here, and they were blocked by getting into the ocean by this huge sheet of ice. And so they backed up and formed big lakes. And those lakes deposited lots of clay that we'll be seeing in some later slides. But we had glacial lake breadths form when the ice was further to the north. And prior to that, we had glacial lake Russell form. Initially, the lake spilled out to the south, and later on, they went out to the north through the present-day Juan de Fuca Straits. So a very interesting change in the landscape here in Vashon. But this last ice advance was just one of many that occurred in the last 2.5 million years during the Pleistocene. Unfortunately, we only have record of about 6 of these advances here in Vashon, and this slide shows about 2.5 million years of stratigraphy with all the different ice advances and interglacials shown here as just a part of what really is a much more complex history shown on the right, which is based on deep sea cores that shows that we had alternating periods of glaciation and melting of ice called interglacials, when it was a lot more like the present day interglacial that we're currently experiencing. If we were to undergo normal Earth processes, we should be starting to go back into another ice age, but that is being postponed by our humans' burning of fossil fuel, creating a lot of carbon dioxide in the atmosphere, changing the Earth's atmosphere from about a little over 250 parts per million carbon dioxide to up over 420 parts per million today. And it's continuing to rise. And as it does, it causes the atmosphere to absorb more heat and create more global warming and a lot of other climatic impacts, like the more intense forest fires and floods and droughts that we're seeing now because of climate change. A lot of glacial and interglacial processes were going on before humans impacted the planet, but we are having a lot more impact than these previous changes that have occurred. In the past, bits of carbon dioxide were erupted out of volcanoes, and when you had enough CO2 build up in the atmosphere, that would cause a little bit of warming, and then you would have more CO2 drawn down and sequestered by shells and trees and other carbon that's buried. And that has been going on for billions of years until man has come in and released just catastrophically a tremendous amount of carbon dioxide into the atmosphere, changing things. So bottom line is we need to change our way and stop burning fossil fuels and use clean energy, in my opinion. So now let's talk about the landscapes that this last glaciation created. On the left, we're looking at a geologic map of Vashon. The colors are all different types of glacial deposits, because that's what occurs at the surface here on Vashon. And on the right, we're looking at a raised relief map of Vashon and the adjacent Puget Sound, which is a 5x vertical exaggeration. So it exaggerates the hills and the valleys. And you can see that we have these huge mega grooves caused by the south moving ice sheet, creating these chains of ridges and valleys that everybody knows about. If you've ever driven on Bank Road or any of our east-west roads, you're going up and down these huge glacial grooves. And then on top of that, we've had rivers like Judd Creek here, carving out Ellisport Creek here, carving out the stream basins that have also changed the topography. So one of the main hazards that we have on Vashon are the landslides that are mostly occurring along the coast, where we have steep slopes, or along some of the ravines in the interior. But mostly where there's steep slopes you have a high probability of landslides when it rains a lot, when it freezes, when you have freeze thaw, all sorts of processes. When there's strong winds that cause trees from the beach or the bluffs to tip over, that can induce a landslide. That you can see that almost the entire coast of Vashon is under a landslide hazard area as far as King County mapping has gone. So one of the great examples of one of these landslides is shown at Lost Lake. There's a blow up of the LiDAR for the Lost Lake area, and you can see the lake right here. Now it's a big peat bog, but you can see the actual fault scarp that this slump block has slid away from, leaving the original fault scarp. Like so, this would be the fault scarp right here, and the slump block is down here, and a little lake has formed if you look at it in cross section. And this shows the main features that control these landslides on Vashon. We have this bed called the Lawton clay, a clay deposit caused by glacial lake sediments settling out, very fine grained clay and silt. And it's impermeable and it's malleable, and it prevents water from going through it. And on top of it, we have permeable glacial outwash. And above that, we have the Vashon Till, which is also known as hardpan, and it's relatively impermeable. It's almost like concrete. But the water flows through the cracks in the Vashon Till and through the matrix, and it eventually gets into the outwash, and it builds up pressure here, and it can't go through the clay, so it builds up enough pressure and it causes failure. And here's a free surface, and that's where most of the failure occurs, on these steep bluffs. And so our bluffs are receding at a rate of about a meter every 10 years. And sometimes the meter can happen in one day, but on average, it's about a meter every 10 years, which is 10 meters, 100 years, and 100 meters, much bigger than a football field, every 1,000 years. So lots of erosion happening, and it's impacting anyone that lives close to a bluff. So not a good place to live, close to the edge of a bluff, in my opinion. If we take another look at the Vashon geology, we can see that the glacial deposits form our aquifers. And here's a cross section, AA prime here, through Burton. And it shows the very uppermost Vashon Till in green, overlying the advanced outwash deposits in blue. This is called our primary aquifer. An aquifer is a bit of rock that is permeable and can store water that we can pump, or the water can communicate with streams at the surface. Eventually, this water will flow out in springs, and a lot of it flows out on springs over in this kind of an area over here because of just water pressure and gravity. But the water actually fills up whole pore space in the aquifer, and it will move depending on the hydrodynamics and the differences in head and water pressure. But the water will move down, and it gets stopped by these aquitards, these layers that are impermeable. These are mostly made of till and silt and clay, whereas the aquifers are made of sand and gravel. So the blue sand and gravel represent our aquifers, and the aquitards stop water from moving and sometimes divert it around. And we have deep aquifers here, which are older gravel and sand beds that were deposited prior to the last glaciation and are used in a lot of water wells to supply water to our surface wells. You can see that as the water interacts with the ocean, you can have seawater that will infiltrate our aquifers. So we have to be careful about over pumping in some of these areas, like close to the coast, because that could cause saltwater incursion. As long as we have enough rain falling on the land and percolating in, we shouldn't have a water problem in the foreseeable future. So right now, over the last 10 or 20 years, there hasn't been a decrease in water table levels on Vashon. So we do not have a current water emergency at all, because we have plenty of rainfall to continue to refill our aquifers. we have a sole source aquifer. The only source is rain and snow that comes from the atmosphere. So if we had a drought for many years and we stopped the rain and snow, then we would have problems. But as long as the rain and snow keeps filling our aquifer, we'll be good. We do have a problem in some parts of the island, though, with water quality and water quality because of the nature of these aquifers. This is highly idealized. They're a lot more complex than is shown here. They're discontinuous, they're thinner and thicker, and in some places, we do have areas on Vashon that do not have the capacity to get water from the subsurface. So it really depends on where you live on Vashon about our water situation. So now let's go on in the field and take a look at what some of these aquifers and aquitards look like. Here's a picture of the two pictures of the Vashon Till, just taken around the corner from my house here at KVI Beach. And it shows the massive till with mostly sand and gravel immersed in this matrix of clay and silt, the really fine gray matrix. And you can see some large blocks over a foot in size. Here's a granite block floating in the till. These were deposited by an advancing ice sheet about 20,000 years ago and dumped on Vashon. These are ice contact deposits showing sands and gravels interlayered. It's faulted here. There's a couple of faults where the ice is squeezing against the outwash and the ice contact deposits. And there's a dog here for scale. She's about 2 feet long. You can go down to southern Vashon to Point Dalco, and you can see peat beds here. And this particular peat bed has been faulted. And here's a fault that juxtaposes this upthrown block. And here's the same peat bed down on the beach where it's been downthrown. Well, actually, this just went up relative to this. And you can see the dark brown or the light brown silt below it on both sides. So this goes from here down to here and then over to here. This is a very interesting peat bed because it's pre-Vashon age. It's probably several 100,000 years old. There's also 100,000-year-old sands here on northern Maury. This is called the Whidbey Formation. These are sands and gravels formed by rivers draining the Cascades during an interglacial period prior to the last ice age. And in this, into the sand, you can find layers of pumice, volcanic ash deposits, and some actual pumice fragments that were blown out of a volcano, possibly either Mount Rainier or Glacier Peak. Some of these pumice fragments can get as large as your fist, and they form these layers. So there was a huge eruption, dumped into the rivers, and that eventually transported them here to Vashon and deposited them. These stream deposits were formed before Vashon was an island. It was part of the mainland, and we did not have a Puget Sound yet. This was a continuous river that drained the Cascades and came all the way to Vashon before it dumped the water into the Pacific. Amazing story preserved here on Maury. You can go to Winghaven or to Point Robinson and see these clay beds. They're finely laminated. You can see the fine layers. These are almost like varves, which are individual annual layers laid down during the seasons, the winter and summer seasons. These clay beds were used to make bricks on the island. And about 100 years ago, there were 11 kilns and brick factories along the coast of Vashon that were using our clay here to make bricks and tile. But they stopped making them about less in the early 1920s not because we ran out of clay, but because they ran out of trees to burn in the kilns, I think, because they had to use a huge quantity of wood, hundreds of cords of wood to burn these kilns to fire the bricks. So you can go to the museum and see some of the great pictures they have of some of the brickworks. But this is the clay that was mined at the time to make the bricks. So now let's move into the beaches and talk about the beach rocks. I thoroughly recommend Ann Spires and others' Vashon Trails book. 5th edition just came out last year, the 15th anniversary edition. And it shows you how to get to all these great beach walks on the island. All these stars are places that have great rocks to look at, mostly at low tide. Here's a picture of Sandy Shores at South Maury with all these residual cobbles. These cobbles came from the glacial deposits. They eroded, the tides and waves eroded the bluffs, and they removed all the sand and silt and clay and left behind the rocks. And that's what we have left here on the beaches. The tides are moving them around, and sometimes you'll see a beach and there's no rocks. They're all covered by sand, but if you wait a couple months, the rocks will be exposed again because of these active drift cells that are occurring. Here's Ellisport KVI Beach at low tide, and you can see all the cobbles here with some sandbars deeper over here to the right. So now let's talk about some of the rocks. The most famous rock that I think has ever been found on Vashon is this mammoth, Columbian mammoth tooth, found by Agnes Lane in 1960 and featured in this article in the Beachcomber. This thing is as big as my head. It weighs 5 pounds. It's 9 inches by 5 inches by 4 inches, and here's 2 different views of it. These teeth are amazing. They're made out of the same stuff our teeth are made out of, apatite, calcium phosphate. And so they're resistant, and this is not really a fossil because it hasn't been replaced by anything. It's an actual piece of the tooth that's on the order of 17,000 years old from this huge mammoth. You can see a picture of what one of these things looked like. They had 13 feet long tusks. You know, you could walk underneath one of these mammoths and not even touch their belly. But these teeth are unique. The mammoths are one of 3 different mammals that have what's called horizontal tooth eruption, where instead of teeth growing up, they grow horizontally and out. Elephants and another mammal also have this horizontal tooth eruption, which is really interesting. But you can see some of the grindings. This is the grinding surface that the mammoth used to grind their grass that they ate. But they would wear down, and eventually a new tooth would erupt out of the back horizontally. So this was collected by Agnes in 1960, and Bob, her son, loaned it to us for this picture. Thanks, Bob. And if you've been to the museum, you've seen the native rock garden and the 3 major types of rocks: igneous, metamorphic, and sedimentary. And we have this great rock cycle where igneous rocks are born of fire, molten magma. They crystallize, they get eroded to form sediments, to form sedimentary rocks that get buried, transformed into metamorphic rocks that sometimes melt to form magma and form igneous rocks. So we have this cycle that's going on. And just to remind everybody, when we say rock, we're really talking about things that are made of minerals, solids. Rock minerals are made of elements, chemical elements in the periodic table, and rocks are grouped in how they're formed in these 3 different groups. And remember that rocks constantly, slowly change over millions of years, and we name rocks based on the minerals present, both the element composition and the texture or their grain size. And so we'll be using a few rock names as we proceed here in the next few slides. Here we have some really cool rocks that you can find on the beach. These are pieces of petrified wood, and here it's been sliced, and you can see what it looks like inside. And here's a piece that hasn't been sliced, and this is what most of them look like. These are really exceptional specimens. It's about 1 foot long here for scale. These 3 were found by Bob Lane and down on Maury at Sandy Shores. And these trees were formed 15 to 25 million years ago, and they were interbeds within volcanic rocks, lava flows. The silica from the basalt weathering percolated through the sediments containing the trees and replaced the cellulose with silica. And so now we have quartz and chalcedony and opal CT forming the petrified wood, making these hard rocks. This is the Washington State gem, and little known fact, petrified wood. So you can go to central Washington to the Ginkgo State Park and see some of these in the field. And somehow either rivers first and then glaciers transported all these petrified wood pieces here to Vashon. All the rocks on Vashon came from somewhere else, just like the people. We're all immigrants, just like the rocks. And it's just the glaciers that brought all the rocks here. Here we have two different groups of rocks. On the left, greenstones, and on the right, andesite and basalt porphyries. Porphyries mean they have big crystals floating in a finer grain ground mass. These are huge crystals that are up to an inch size of feldspar, plagioclase feldspar. And these are basalts and andesites. Some of them are reddened by oxidation of iron. These formed in volcanoes and as lavas and domes from the Cascades. In the last million to up to 20 million years ago, we've had formation of these volcanoes, erupting these volcanic rocks that get eroded and dumped into the rivers and then finally transported by glaciers here. The greenstones are bits of Silesia that I mentioned early on. And as you can see, they're green for the most part because of the mineral chlorite. They've been metamorphosed. These formed as submarine lavas 56 million years ago in the Pacific, and they were later metamorphosed, buried, and then transported to the North American plate to form our basement. You can see pillow lavas here. Here's a pillow bread crust bomb, and here's the edge of one of the pillows. Just fantastic textures. Here's what's called a turtle rock that you can find all over the Pacific Northwest on the beaches. And this is caused by devitrification of the basalt glass that creates these spots. Very interesting textures. If the igneous rocks slowly cool, they form granites or gabbros or monzonites or different igneous rocks, coarse-grained igneous rocks, big crystals that you can see with your eye. They could be white, they could be pink. The pink is caused by potassium feldspar, and they have all different colors and different grain sizes and textures. Sometimes you find black xenoliths. These are fragments of the country rock that incorporated into the magma chamber that the granite crystallized from. And so these are the bowels of Cascade volcanoes. These are intrusive igneous rocks that form some of our diverse Vashon beach cobbles population. We also have chert. Chert is a rock composed of silica, just like quartz. In fact, you can see some of the quartz veins here. Chert comes as black or gray or red or orange or green, all different colors. And these are metamorphic rocks. They started out as planktonic skeletal skeletons that rained down on the seafloor as the radiolaria and diatoms died, formed this silicious ooze on the seafloor. That was buried and then eventually metamorphosed to form these quartz veins. And then that was later eroded and uplifted and then transported here by glaciers. So amazing story that these cherts, these are as old as 160 million years. The Orcas chert that's found up in the San Juan Islands is probably the source of most of these. But the oldest rocks on Vashon are as old as 1.3 billion years old, these Cambrian to Precambrian quartzites. They started out as sandstones deposited on shorelines or in deserts long ago in North America. They got buried, metamorphosed, transformed into these quartzites, these gray and orange and buff reddish rocks that are just tiny quartz grains all crushed together and recrystallize into a dense quartzite. Sometimes there'll be little quartz veins in them. You can see here in a few of them. But for the most part, the brown is due to a little bit of mineral matter and iron minerals. So 1.3 billion year old quartzites on our beaches here, transported from British Columbia all the way down to Vashon. We have sedimentary beach cobbles. They can be conglomerates or breccias. sandstones, turbidites. These were mostly from the Olympic Mountains accretionary complex. Remember where the two plates collide, the Juan de Fuca plate, the sediments are scraped off into the trench, and that trench is buried and deformed, and it's squeezed and turned into these really interesting cobbles of sedimentary turbidites. But by far, I think the coolest rocks are the mantle rocks, these serpentinized peridotite. These come from the Fidalgo complex up near Anacortes and northern Whidbey Islands. They are pieces of the Earth's upper mantle that we have here on Vashon, transported by glaciers, but originally exposed at the surface up in the San Juans and northern Whidbey. And then the glaciers dragged them down here, eroded them and dragged them here for us to find on the beach. We also have some other gemstones, nephrite jade. If you made a thin section of it, this is about 1 millimeter thick. This is what it would look like, this beautiful green jade. And this is what they look like right on the beach. These are from Bob Lane's collection. He found them. Yeah, they're pretty rare, so it's hard to find them. I found a few pieces like this, but in the last 5 years. But keep your eye open for really hard green rocks. They tend to be veined and sort of different colors, different shades of green, but they're really hard. Jadeite is a high pressure form of basalt where it's metamorphosed at high pressure and low temperature, and it's really hard. So it's preserved and they can withstand a lot of weathering. So if anyone has been to the Point Hayer rockery, they've seen this evolve in the last year. This is looking north from just north of the radar tower, the radio tower. It started out as this fun little pile of rocks with a big piece of the Fidalgo peridotite here in the middle and some other cool rocks. And then in the last year, it's grown, and people contributed all sorts of cool rocks and cairns and made artworks. And here it was this morning at high tide at about 9 o'clock. When the tides are messing with it and have totally transformed it. And this is the beauty of this construction, because it's dynamic and it's changing, and it's showing us how cool rocks can get transformed, yet get preserved for us to rebuild again tomorrow. Here we are back in September when some kids here are making some really cool constructs. You can also do similar building of cool artworks at the museum in our little sandbox. So we have 4 basic concepts I'd like to leave you with today. The Earth has a long history. 4 billion years is 4.5 billion years is really hard to comprehend. And I think we have to remember that, and that we're just a little blip in the long history that's happened before us. And it's humbling that we've inherited this amazing history of a planet. And this planet is constantly changing. We live on an active planet due to this process of plate tectonics and the interaction of all these Earth systems. Some of these changes are really fast, others are slow. Nothing on our planet is permanent. And we really need to understand present day Earth processes to unravel the past. However, not all present day Earth processes have happened. We have past processes that are not happening today, and we need to study the rock record to understand those processes. You know, when the Chicxulub crater formed in 65 million years ago in northern Mexico to form this huge crater and a huge tsunami that killed the dinosaurs and flooded North America and created havoc. We're talking 100-meter high waves that inundated the whole coast. That process has not been observed. So uniformitarianism isn't totally true. There are some processes that we don't see today that are present in the rock record. And we should all remember that all societies and inhabitants exist at the mercy of Earth processes. We depend on Earth resources, and we're vulnerable to the hazards on the Earth. And our impact on the planet has changed this natural course, as we mentioned. We now need to correct for these impacts by healing the Earth for future generations. or they will suffer the consequences. We don't need to save the planet, yet we might save ourselves if we act. I think that's a really important point. The planet's going to survive without mankind and humankind. It's going to change a lot, but if we want to see humans survive in the future, we need to do something to preserve it. And there's all sorts of resources available. The 9 big ideas. You can go to earthscienceliteracy.org and see these concepts that I think every citizen that lives on this planet should know very well. I wish you all a very happy New Year. The Washington DNR sent out this New Year greeting with 2023 LiDAR images, all from Washington, none from particular Vashon, unfortunately, but Washington has an amazing diversity of landscapes, and the natural beauty is just overwhelming. And to close, I thank all of my collaborators, especially Tom DeVries and the Natural Wonders curators, Bianca and Maria and others, and also my friends at the Vashon Union of Geologists. We have a core group of 30 or so geologists here on Vashon. So thank you everyone for all your help and collaboration. And here we are looking on January 2nd at the sun rising over Mount Rainier from my porch. We live on a very dynamic Vashon with an active plate boundary right below us. We have a rich geologic history and diverse rocks. And I welcome you to visit the museum and see just a taste of the diversity that we have here on Vashon. So thanks very much for participating, and I'm happy to answer any questions.
Yeah, this is a time for everyone you could post questions in the chat. Better to do it there than in the Q&A function of Zoom. I could start out with a couple of the questions while people may be thinking some other ones, additional ones, or ones that were posted earlier. First of all, attendees were interested, one attendee was interested in particular in the app that you mentioned early in the presentation. Maybe you could type that in the chat, Steve, if you wouldn't mind.
Sure, it's called Earth Viewer. If you just Google Earth Viewer, you'll find it.
Okay, thank you. And then I think another question was about 2 questions that were posted. One is, why is the center of the Earth so hot? And also there was a question about where do agates come from? I didn't hear any particular references directly to agates, and there's many people on the island who are interested in finding agates and the like.
Yeah, I didn't really have time to get into the details of agates. I should have mentioned them, but that's another form of silica. Agates form from voids or cavities in volcanic rocks, and the silica has migrated through fluids and precipitated to form the agate that forms thunder eggs and all sorts of other forms of silica. And it's a form of quartz, so it's really hard, and you can cut and polish it. They're really beautiful, and so those are formed mostly in volcanic rocks. If you've seen the amethyst geodes, the big, huge cavities, those come from South America mostly, from the Paraná basalts that are about 130 million years old. Big, huge cavities of amethyst caused by silica precipitating to form those beautiful purple quartz crystals. The reason the center of the Earth is as hot as the surface of the sun is because of collisions of the planetesimals that form the Earth when all these big pieces of planets that as the solar system formed, you had bits of planets floating around and around the sun, and gravity would pull them together, and that would create a huge amount of energy. They would melt on impact, and they would stay hot. And as you continued to add more material to form, as the Earth grew, it kept the heat in the middle. There's also a little bit of radioactivity in the mantle and crust. Potassium, uranium, and thorium are decaying, and that generates heat, but that only accounts for a small fraction of the heat flow and the high temperatures that occur in the very center of the Earth. The Earth has been cooling in the last 4.5 billion years. Eventually, it's going to freeze, and we won't have a liquid inner core or liquid outer core and a convecting mantle. Will be like a dead planet, like Mars or some of the other rocky planets that don't have plate tectonics, as far as we know. So yeah, it's a very good question about why it's so hot, but there's a very good explanation for it, and it's been verified with calculations and models and other methods. So what other questions?
So first of all, there's a lot of congratulations, Steve. It's really, people really enjoyed it. There's one here from Jules. Somebody said, some of my favorite rocks to find are ones that are half one thing and half another. What are all the different ways these are formed? I found so many different combinations.
So yeah, there's contacts between different layers that could be what you're talking about. I showed some of the xenoliths, the black rock immersed in a granite. That could form another contact, and you could just have the erosion giving you the juxtaposition of two pieces of something that's very different if it was a much larger mass. But as the rock gets weathered down and eroded down into tiny pieces, you sometimes, just because of happenstance, form two different types of rocks right in one. It's really cool. And each one has a different story. And I'd be happy if you wanted to bring them into the museum, or we could have a meeting. I'd be glad to give you my interpretation of why they are the way they are.
Great. I think there's another, is there a place on the island where we can see all three layers? Lawton to Vashon Till.
Yeah, there's a bunch of places. In fact, we have some older deposits. I didn't really have time to get into it, but we have older glacial lake deposits up by Winghaven. They're actually pre-Lawton clay. They're probably over 780,000 years old because they're reversely magnetized. And so they were formed from an earlier glacial lake that long predated the last advance. But you can go to near Dilworth. There's some really nice clay overlain by till. We don't have, if you go to Maury, it's mostly outwash on Maury with some clay below. There isn't much Vashon Till there on the, but there are places, and it's just a matter of looking at the geologic map. There's some great geologic maps that show all the different surface exposures of the different units.
Here's a question from Rich. I had a new septic tank installed. The installer said there was volcanic ash layer about 5 to 7 feet below the surface. I'm near the school campus at the top of Vashon. Do you have a guess what volcanic eruptions caused this? The volcanic ash layer that's 5 to 7 feet below the surface.
Well, it could be one of those pumice layers that I showed you that was in the Whidbey Formation. We'd have to see exactly where you're located, and I'd love to see the data that your well log from drilling the water well. It'd be really cool. I'd like to learn more about it. Yeah, we're in search of volcanic ash beds here on Vashon because they are nice little timelines that you can use to date stuff. And we've got plenty of eruptions from Mount Rainier, Mount Baker, Mount St. Helens, Glacier Peak in the last several 100,000 years that we could draw on to try to date the sediments.
Great. Other question here is, why didn't the land that is Vashon get scraped away by glacial retreat like the rest of the sound?
So it turns out that the sound actually was carved out not by the glacier itself, but by rivers underneath the ice sheet. Derek Booth from UW figured this out about 30 years ago. And it's sort of counterintuitive because you'd think that the ice was just gouging out the deeper sound, but it was really rivers that were flowing underneath. And actually, because the ice was thicker up to the north, the rivers flowed uphill underneath the ice because it's following hydrodynamics and it's seeking lower pressure. And so each time the ice sheet advanced, it carved out some of the pre-existing rocks, and then as it retreated, and sometimes as it's moving and advancing, it's depositing rocks underneath it that don't get eroded away. So it's both eroding and depositing. And then when the ice retreats, it actually just leaves whatever is on top of it and within it on the ground. It just dumps it. It's like when the snow melts in the Driftway parking lot in the winter in those big piles, and all the black stuff, all the dirt just settles out at the top. I mean, that's sort of like the recessional outwash that occurred 15,000 years ago. But yeah, we have several different glacial deposits from several different ice advances preserved on Vashon, but it's highly variable where you can preserve the complete record of all the different advances.
How do we figure out how rocks are formed?
By studying them, we can chemically analyze them. We can make thin sections that are 30 microns thick and look at them through the microscope. And we can do experiments in the lab to try to duplicate what they look like. And that tells us what kind of conditions they formed in. There's all sorts of ways of analyzing them and characterizing them. And I'd be glad to provide some books to explain that. I'll put my email in the chat, and feel free to send me an email and I'll link you to some stuff. We do have on the website, I believe, some resources. There's a fact sheet on Vashon Geology that you can download that has a lot of resources as well.
Okay, Terry has the question, how was Quartermaster Harbor formed?
Oh, that's a good question. I mean, ultimately, it's the glaciers, and we just had a lot more sediment left on either side of it, and less. And there was probably rivers that could have eroded a lot out, like Judd Creek could have originally drained all the way out at the southern tip of Vashon and Maury. That's probably the simplest explanation. That you started out with a continuous. If you go over here to this map, a continuous river that went all the way down here, and as sea level rose, it flooded a bit of the drainage. But ultimately, it's just the way the glaciers operated and where they dumped stuff and where they eroded stuff, because we have these huge grooves that you saw in the images earlier.
And we have one last question from Jewel. She said, I'm really interested in geology, and next year I'll be studying at the UW. How can I get involved with geology stuff on the island right now? I would love to talk to some more people with lived experience in geology.
Well, you've come to the right place, because we have 30 geoscientists who live on the island, and we're part of this informal organization called VUG, which is sort of a play on words, because a VUG is a vesicle in a lava. And so, but it also means the Vashon Union of Geologists. And we meet periodically, a couple times a year, and we'd be glad to talk to you. We can do it in a small group, or we can do it. We haven't really scheduled our next VUG meeting. We need to do it this spring sometimes. So just send me an email. I put my email in the chat there, and we can put you on our list, and let you know.
Okay, and I think I'm gonna, after Ken's last question, we're gonna close it because it's already almost 20 after. But Steve, have you heard of the CAR report available at the library, a study of our island water availability?
Yes, I have. And there have been a number of water studies on Vashon. The Groundwater Protection Committee is currently studying this, and they are the experts on the island who I would recommend contacting for any questions that you have about our water availability. But the CAR report is definitely worth reading, and there's a number of other water-related reports that the county has funded that you can also read. And if you send me an email, I can send you links to them all. They're all available for downloading at the county website. And if we didn't get to any all the questions, just send me an email. I'm happy to answer them. But I'd love to hear more about this volcanic ash layer below the surface from Rich. So please send me an email, Rich.
Thank
Okay.
you, Steve and Patrick. I'm sorry, Patrick, go ahead.
No, I think I just wanted to give a round of applause to Steve. You're getting accolades in the chat. And I think there has been questions about whether the slide deck will be shared, and I'll let Elsa and Steve respond to those questions.
Yeah, I'm happy to share the slide deck and we can post it so you can download it if you want. The recording will also be available, I believe. So we can go both ways if you like.
Okay, I would like you to share the slide deck, Steve, and
Okay.
but we will have the, if you want to, and then we will have the, as I've said, the recording on the website by probably early next week. Thank you, Steve. This has just been a tremendous talk this evening, and it sounds like when the weather turns nice, or if you want to stand in the rain, that we should arrange to have some talks at the museum at the Garden of the Ancients, which you curated at the Natural Wonder Museum at the.
Happy to do that. Yeah.
Thank you very, very much. And next month, we'll have Tom DeVries will be here speaking about ecology. And so everybody tune in next month. Thank you.